The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. In this video, I would like to explain the difference between the formation of new oceanic crust and new lithospheric mantle, starting from the spreading zone. Both together form the oceanic lithosphere, which drifts away from the spreading center, being the base for the ocean, which is getting wider and wider. As with all other videos, I would like to point out the opportunity giving me feedback if you have any questions or comments. You will find my email address on the first page of this video or on the website. This figure shows the situation at a spreading zone without any exaggeration. And we are now concentrating on the top area and have a look what's happening directly at the fissure that repeatedly keeps up opening in the spreading zone. As I mentioned in one of the first videos, here we cannot see very much without exaggeration. Therefore, I will zoom into this area and exaggerate a lot. The formation of oceanic crust occurs in the uppermost kilometers, where the crust is 5 to 8 kilometers thick on average. At the opening gap, the oceanic crust is built up to its final thickness and composition. In this figure, you can see that the thickness of the crust no longer changes on either side. And this is one of the most important differences compared to the formation of the lithospheric mantle. The lithospheric mantle is composed of exactly the same material as the asthenosphere. The only difference is partial melting of the asthenosphere, which then makes it flowable. The two small illustrations on the right show how you can imagine partial melting. The rectangles show highly enlarged sections of the asthenosphere at the points where the small rectangles can be seen in the asthenosphere below, their spreading center and further down. The edge length of such a rectangle would be a few millimeters or centimeters. The bright areas in this enlargement consist of molten rock, while the darker areas are in a crystalline state and solid. So these could be olivine crystals, for example. The amount of partial melting depends on the depth at which the asthenosphere is located. The pressure decreases upwards simply because the overlay becomes smaller. There is less weight on top. This decrease in pressure plays a crucial role because it contributes significantly to the fact that the melt proportion increases considerably towards the top. This is called the decompression melt. The melting process is caused solely by the decreasing pressure, the decompression, when the mantle material rises. No additional heat or other processes that endorse melting are required. In some cases, the rate of partial melting at shallow depth directly beneath the spreading zone can increase to more than 25%. And these partial melts ultimately feed the magma chambers beneath the spreading zone from which the oceanic crust is finally formed. The lithospheric mantle, on the other hand, does not evolve from a magma chamber beneath the spreading zone from which the oceanic crust is formed. As the newly formed oceanic crust drifts away from the spreading center, both the oceanic crust and the underlying asthenosphere gradually cool. However, when it cools, the asthenosphere turns into lithospheric mantle because when the molten parts are crystallized, the rock is solid and then it's part of the lithospheric mantle. As a result of this cooling, the lithospheric mantle continually thickens downward as it drifts away from the spreading center. That is why the lower boundary of the lithosphere is not as sharp as the boundary between the crust and mantle, where there is a clear change in material. That is the MOHO, the famous Mohorovičić discontinuity, which is the seismic boundary between crust and mantle. The cooling process in the beginning occurs relatively quick, but then becomes slower, and the thickening of the lithosphere also slows down accordingly. It continues over a long period of time, and it is assumed that it needs around 80 to 100 million years to reach a point after which there is no longer any noticeable thickening, although the process continues very slowly. This figure shows the age structure of the lithosphere and shows the difference between oceanic crust aging with distance from the spreading center, while the lithospheric mantle decreases in age downward. In this non-exaggerated representation, the age relation is clearly demonstrated. With the exaggerated representation, which I show again here, it is harder to understand. The lithospheric mantle in the upper parts is already several tens of millions of years old at the edge of this image, while it is just forming at the base. In any case, this is a bit of a problem when you work with exaggerated representations. Such a representation makes some relations clearer, such as, for instance, the structure of the lithosphere, but if you look at the development of the lithosphere over time, as is the case here, the exaggeration can also be hindering. The gradual increase in the thickness of the lithospheric mantle has another important and, above all, visible consequence, which I will discuss in the next video. It's about the increasing thickness and density of the lithosphere, I mean oceanic crust and lithospheric mantle together. This time, thank you for listening, and I'll be happy if you stick around. And I recommend continuing with the video on aging of the oceanic lithosphere.